The dynamical system concept is a mathematical formalization for any fixed rule, which describes the time dependence of a point's position in its ambient space. The concept unifies very different types of such rules in mathematics. The different choices made for how time is measured and the special properties of the ambient space may give an idea of the vastness of the class of objects described by this concept. Time can be measured by integers, by real or complex numbers, or can be a more general algebraic object, losing the memory of its physical origin. And the ambient space may be simply a set, without the need of a smooth space-time structure defined on it. Formal definition. There are two classes of definitions for a dynamical system. One is motivated by ordinary differential equations and is geometrical in flavor, and the other is motivated by ergodic theory and is measure theoretical in flavor. The measure-theoretical definitions assume the existence of a measure-preserving transformation. This appears to exclude dissipative systems, as in a dissipative system a small region of phase space shrinks under time evolution. A simple construction shows that it is always possible to construct a measure so as to make the evolution rule of the dynamical system a measure-preserving transformation. In the construction, a given measure of the state space is summed for all future points of a trajectory, assuring the invariance. The difficulty in constructing the natural measure for a dynamical system makes it difficult to develop ergodic theory starting from differential equations. So it becomes convenient to have a dynamical system's motivated definition within ergodic theory that sidesteps the choice of measure. General definition. In the most general sense, a dynamical system is a tuple where T is a monoid, written additively. M is a set and phi is a function with for the function phi is called the evolution function of the dynamical system. It associates to every point in the set M a unique image, depending on the variable T, called the evolution parameter. M is called phase space or state space, while the variable x represents an initial state of the system. We often write if we take one of the variables as constant, is called flow through x and its graph trajectory through x. The set is called orbit through x. Note that the orbit through x is the image of the flow through x. A subset S of the state space M is called phi invariant if for all x in S and all t in T in particular, for S to be phi invariant, we require that I equals T for all x in S. That is, the flow through x should be defined for all time for every element of S. Geometrical cases. In the following cases, M is a manifold. Dynamical systems are defined as tuples of which one element is a manifold. Real dynamical system A, real dynamical system, real-time dynamical system, continuous time dynamical system. All flow is a tuple with T an open interval in the real numbers R, M a manifold locally diffeomorphic to a Banach space, and phi a continuous function. If T equals R, we call the system global. If T is restricted to the non-negative rails, we call the system a semiflow. If phi is continuously differentiable, we say the system is a differentiable dynamical system. If the manifold M is locally diffeomorphic to Rn, the dynamical system is finite dimensional. If not, the dynamical system is infinite dimensional. Discrete dynamical system A, discrete dynamical system, discrete time dynamical system, map or cascade is a tuple where T is the set of integers. M is a manifold locally diffeomorphic to a Banach space, and phi is a function. If T is restricted to the non-negative integers, we call the system a semi-cascade. Cellular automaton. A cellular automaton is a tuple with T a lattice such as the integers or a higher dimensional integer grid. M a function from an integer lattice to a finite set, and phi a evolution function. As such, cellular automata are dynamical systems. The lattice in M represents the space lattice, while the one in T represents the time lattice. Measure theoretical definition. See main article Measure preserving dynamical system. A dynamical system may be defined formally as a measure preserving transformation of a sigma algebra. The triplet phi here, T is a monoid, X is a set, and is a probability space. A map phi XX is said to be sigma measurable if and only if, for every sigma in sigma, one has phi minus 1 sigma. A map phi is said to preserve the measure if and only if, for every sigma in sigma, one has mu equals mu. Combining the above, a map phi is said to be a measure preserving transformation of X. If it is a map from X to itself, it is sigma measurable, and is measure preserving. The triplet phi for such a phi is then defined to be a dynamical system. The map phi embodies the time evolution of the dynamical system. Thus, for discrete dynamical systems the iterates for every integer n are studied. For continuous dynamical systems, the map phi is understood to be finite time evolution map and the construction is more complicated. Relation to geometric definition. Many different invariant measures can be associated to any one evolution rule. In ergodic theory the choice is assumed made, but if the dynamical system is given by a system of differential equations the appropriate measure must be determined. Some systems have a natural measure, such as the Liouville measure in Hamiltonian systems, chosen over other invariant measures, such as the measures supported on periodic orbits of the Hamiltonian system. For many dissipative chaotic systems the choice of invariant measure is technically more challenging. The measure needs to be supported on the attractor, but attractors have zero Lebesgue measure and the invariant measures must be singular with respect to the Lebesgue measure. For hyperbolic dynamical systems, the sine-Iru-Bowen measures appear to be the natural choice. They are constructed on the geometrical structure of stable and unstable manifolds of the dynamical system. They behave physically under small perturbations, and they explain many of the observed statistics of hyperbolic systems. Construction of dynamical systems. The concept of evolution in time is central to the theory of dynamical systems as seen in the previous sections. The basic reason for this fact is that the starting motivation of the theory was the study of time behavior of classical mechanical systems. That is the study of the initial value problems for their describing systems of ordinary differential equations, where represents the velocity of the material point x. V t times mm is a vector field in Rn or Cn and represents the change of velocity induced by the known forces acting on the given material point. Depending on the properties of this vector field, the mechanical system is called autonomous when V equals V, homogeneous when V equals 0 for all t. The solution is the evolution function already introduced in above. Some formal manipulation of the system of differential equations shown above gives a more general form of equations a dynamical system must satisfy, whereas a functional from the set of evolution functions to the field of the complex numbers. Compactification of a dynamical system. Given a global dynamical system on a locally compact and Hausdorff topological space X, it is often useful to study the continuous extension phi asterisk of phi to the one-point compactification x asterisk of x. Although we lose the differential structure of the original system, we can now use compactness arguments to analyze the new system. In compact dynamical systems, the limit set of any orbit is non-empty, compact and simply connected.